Okay, let's now begin the lecture. Before we officially study the chapter 2 of the Griffins, I would like to get a review of what we have learned before in the lecture 1. It's about some mixture of the parts that we have learned. So basically, we've learned the integral by parts, and right now, what I want to do is to generalize that from 1D to 3D. So I think you might be familiar with the expressions here. That these are what I just talked about in the previous lecture. Now, to see that what we want to do is to generalize to 3D. So the integral is no longer of one variable x, but it could be a three-dimensional integral. So the dx will be replaced by a d tau, and the d tau is the volume element. Now let's see. We actually can do a similar thing that we first record that in the 3D differential analysis, there is also the chain rule, and so say that if we want to calculate the divergence of scalar times a vector, we can apply this divergence to the vector first, and then multiply by the scalar, or we can apply the del operator to the scalar, which gives the vector quantity, and we dot this vector with a again. So this is similar to the chain rule, and now we do the same trick, that is do an integration of this for the both sides. And if we do the if we do a volume integral on the left side, it actually we can actually use the same divergence theorem, and here the divergence theorem for A is shown here, and we can simply replace A by the FA. And now if we combine this, we can I can try to write them down. So integral of del dot fa, which is on the left hand side, equals yes, I think this is should be a, so it should be fa dot da on the left hand side, and on the right hand side, f del dot a integral v d tau, and the second term is integral v of a dot del f. And now this means that say that we can we are interested in this term, but we might not know how to calculate that. Then we simply write this as the term here minus the term over here. So it will be and here in this way we transform this this term that sometimes we might not be able to do this, and we transform this divergence operator to a gradient operator acting on the scalar, and this volume integral, this surface integral, is the additional thing that we need to add. Okay, so I've simply copied the things over here, and now we can try to do an example. For example, the integral here, we might not be able to calculate this del dot r hat over r square, and if that's the case, we can try to move this del to the left, and let's apply this example. So here this volume integral of fr del dot r hat over r square d tau. D tau is the volume element, and can be first written down as the volume integral of a dot. Sorry, so this a should be r hat over r square and dot del fr, and we do this volume integral plus the second term is the surface integral, which is fr times r hat over r square dA. Now to get the first term, we simply apply the chain rule. So partial fr partial r, and there is additional. Let's work this out maybe on the side here. So del fr should be x hat partial x plus y hat partial y plus z hat partial z applied on fr. And the first term can be worked out like partial x of fr, and now we can use the chain rule. So partial x can be written as partial r of fr, and partial r partial x. So here the partial r partial x should be square root of x squared plus y squared plus z squared partial x. So it's 1/2 x over r. Did I do it correctly? Okay, so let me know if I did anything wrong, and so I can try to correct. And so this term in the end, by combining all the terms together, gives x hat x over r plus y hat y over r plus z hat z over r, and additional f derivative of f. Okay, and so now we work out this first term, and so let's rewrite this down. So these three terms can be actually written as r hat times f prime r, right? Because on the denominator, x hat, y hat, z hat is simply the r vector, and that's by definition. And if you divide by r vector by additional r in the denominator, it will give you the r direction. And so it's r hat f prime r. Okay, so we've finished. We've simplified the first term and done the derivative, and now the second term we can try to work it out. And so here we are trying to calculate the integral over a sphere, and so the sphere has a given radius of r. So I'm trying to draw the 2D section, And so it's best to do the integral in spherical coordinates, right? And so let's write out the integrals in spherical coordinates. Let me first try to copy this down. Okay, so in the spherical coordinates, the integral of v can be written down as a triple integral, right? So it's integrate r from 0 to r, and integrate theta from 0 to pi, integrate phi from 0 to 2 pi. And then we write down the what's inside. So r hat dot r hat equals 0. So we can simply equals 1. So we can simply ignore this term, and what's left over in the integrand is f prime over r squared. And now the d tau is the volume element. So if you look up of the table, if we, in the spherical coordinates, the volume element is simply r squared sine theta, and d phi d theta d r, and the r squared also cancels each other. And if you do this integral, you can see that this one simply gives you only a single integral of r, which that we need to deal with later. And let's look at the second term. Let's look at the second surface integral. So the surface integral should be only integral of theta and phi, because the r is kept as a constant, and we are looking at the integral of the surface, which with a constant r. So here this integral should be written as theta from 0 to pi, phi from 0 to 2 pi, and we keep this term here, fr, and here the r hat direction is actually perpendicular to the surface. So the r hat dot dA, the area, the normal direction of the area is actually equal to 1. So we can also drop the r hat, and what's remain is 1 over r squared. And the area, there is also integral sine theta that you need to consider, and you again is d phi d theta. And now let's continue the calculation. So the first term gives if we simplify the second and third integral, the r squared on the bottom is already left, and f prime r partial integrate over r, and we can separate out the integral of theta, and this phi. So this integral gives 2. This integral gives 2 pi, and this integral actually gives back the f function, and this is fr minus f0, right? And so the first one we've already worked it out, and now the second term is again we do a similar thing. So let's look at the theta and the phi. Oh. So I think I should miss the R square somewhere here. Let me see. I think that should be the volume element that also contains the R square term, and because the surface integral, you can imagine that the dA is also should be proportional to the R square, because as your R becomes large, the surface also becomes larger, so the dA also proportionally to the R square. And now if we fix that, then this R square also cancels the R square here. And what's left over is in the R direction is the FR itself. And in the theta direction, again, it's 0 to pi. Okay, so this FR should be evaluated at R equals capital R. So this R should be capital R. And in the theta direction, it should be sine theta, d theta. And in the phi direction, it should be again. So again, this gives 2. This gives 2 pi. And you actually see that this term also cancels out this term. And what's left over is simply F0 times 4 pi. Right, so the final result is actually pretty simple. And now let's look at this problem again. So in the homework 4, you actually try to work out. So I will give you this slides later, so you can get a copy of this later. So if you so you don't need to take pictures of this, and also the session is being recorded, and so don't worry if you are missing a moment to capture something. So here, if we look at this gradient applying on this R hat over R square, we actually already worked this out in the question 4 of the homework problem. So if some of you have already done the homework, then you might be already familiar with that. So the conclusion is that if we apply this del dot R hat over R square, and we can actually simply get a 0 for all this R that's not equal to 0. And so this result is not quite that not quite makes sense, because if you plug if you plug FR equals 1, and what you get is simply integral of del dot R hat and R squared d tau, right? And this function is actually 4 pi. And this the integrand itself integrand itself actually somehow is 0 everywhere except at R equals 0. So could you think of some function that actually satisfy these rules? Is there any function that somehow it's 0 everywhere, and if you do a volume integral, it gives you a finite number. But there is a caveat, right? That at R equals 0, the function might explode, because if you plug R equals 0 at here, this function is an exploding function. So any of you have an idea of how to get this kind of function? Or are you familiar with this function? So let me summarize what we find, right? So let's note. Let's note this is a function of gr, right? So define this gr. What kind of the property is that gr is actually 0 if r is not 0, and it's infinite when r is exactly at 0. And if you do a volume integral that includes the 0 point, this gr actually gives you a finite number. So the answer is the direct delta function. So I don't know if you learned this from physics 2051 before. So it's an optional learning material, so I'm not exactly sure if whether this part is being touched. So did you learn the delta function in one-dimensional? Okay, no, so all of you haven't learned this. Okay. Okay, then I'll give you more introduction to this delta function. So this delta function is very, technically speaking, not an ordinary function. But you can try to think of this delta function as a limit. So imagine that here we have this kind of step function, right? And now this step function, we make a requirement such that the integral of this step function should always be kept as a constant 1. But somehow we keep reducing the step width. Let's keep this width as d. Now we denote this g as the function of d and x, right? And if we take the limit of d go to 0, and this g dx is actually going to be a strange function. So we call this as a delta function. And what this one behaves is it will get sharper and sharper, right? So so it could be this sharp, and eventually there is only a single spike that is extremely narrow, and this spike will definitely go to infinity, right? And but this infinity, if you do an integral of that, that actually gives you a finite number, and this is defined as the one-dimensional delta function. And so you can see that here on the 2051 notes, I don't know if even if it's optional, you might still be able to look up the notes. It might still in your notes. And so here for this delta function, again it's similar, right? So this delta x is x minus x prime is 0 everywhere, except at this x prime position where it's infinite. And this, however, is not a complete definition, because you don't know how sharp, like how infinite is this infinite. And what really defines this delta function is the additional constraint that if you integrate out this delta function, it gives you 1. And it's not any other number. So, but previously what we get is not exactly 1, right? So this is actually 4 pi times the delta function. And also we have a 3-dimensional function, like the function depends on x, y, and z. So this is a 3-dimensional delta function. You can write out also in terms of delta x minus 0, delta y minus 0, delta z minus 0. So really you have to let both x, y, and z go to 0. then you get infinite value here. Okay, so this is the so this is the basic introduction of this direct delta function, and there are also some properties of this delta function. So the most important properties that I want you to know is that if you integrate sorry. If we multiply this delta function with the additional f of x, and this actually gives you the f of x prime. So you can think of this delta function. What this delta function does is to sample the f of x and only take out the value at x prime. So magically it changes fx to fx prime. Okay, I will give you probably some more examples on direct delta function later, since you haven't learned that. And but for now, let's go to the physics part. And so here in the electrostatics part I'm sorry. So in the electrostatic part, there are two experimental observations. The first is the Coulomb law. We just talked about the Coulomb law before. In the lecture 1, right? And the second is the superposition principle. Could you hold on for 1 second? Sorry. So what the Coulomb law consider is only one single source charge and one single test charge, right? And so here, if I draw this, it will be one single source charge at Q, of charge Q, which has position R prime, and another test charge of capital Q sitting over here at R. And here, this curly R is simply by definition is R minus R prime. And what's the principle of the superposition says that the force, the test charge fields, can be simply find out if you sum all these forces from all the source charges. Say there is Q1 at this position, there is another Q2, Q3. How to get the total force is simply by summation. And this is not a trivial thing. And this is observed from experiment. And so we can treat this as a definition. And somehow next, what we want to do is to find out information based on these two experimental observations. Now, before we do that, let's go through an example. And the first example that I want to do is to find out say that there is two charge, right? That's the simplest situation. Two charge, one is of Q, another is also of charge Q. And the simplest problem is on a straight line, right? and they are separated by a position D. And say that we are interested in finding out what's the force and what's the corresponding electric field at this location where there is a separation of X. And say that this is defined as an origin 0. And now we can write out the electric field as the contribution from the charge at the center. So this is the for 4 pi epsilon naught, and you should use Q divided by R squared, right? So R squared here is X squared, and it's pointing along the X direction. And then there is the second term, right? You simply write down Q over X plus D squared, and it's also at the X hat direction. And now we can simply sum up this together, and that gives the final answer. And now when we are physicists, when we are doing problems, we don't unlike mathematicians that this might be the end. So what we want to do is try to have a sanity check to see, like, also try to do that the same. Try to do the same in your homeworks or in your exams. So you can check whether your answers make sense by doing some analysis, right? Say we can take the x goes to infinity limit, and in this limit the d drops out, right? And so the E simply goes twice of Q x squared x hat. And this means that if we are really far away from these 2-point charges, the 2-point charge actually looks like one single charge of charge 2Q, right? And now let's do a similar problem, but slightly different. That is, we replace this Q by minus Q and see what happens. Again, the distance are still the same, and we are interested in the E field here. So here, what this one is simply giving, instead of this plus sign, here what we need is a minus sign, and that should give us the answer, right? And now if we do this, if we write down this explicitly, we get x squared x plus d squared, and here the x squared cancels, and only the 2xd plus d squared, and along the x hat direction. Now again, if we do the same thing and let x go to infinite and see what happens, now we can see that here this the one that inside does not look exactly like 1 over x squared, and it looks like 2 over x cubed, right? And this is slightly different from what we saw earlier in the example above, right? And but think about this. So if we have two charges that's far away from us, and if they are the same sign, the charge is 2q, right? And however, why if we change one of the charge to minus q, the answer is not 0? So imagine that what we know from the first one should also apply to the second one, right? So naively thinking, this should give us a 0. So why it's not 0? So anyone have a guess? Can you say it louder? Sorry, so I didn't hear, but yes. So if we think physically, actually, I would say that if you say that the answer is 0, I would say that you are mostly correct already. And here, this x cubed, if you compare if you can compare the order of magnitude of these two answers, the first one is much larger than the second one, right? Because we are considering the infinite x limit. And so the second answer is pretty much 0 comparing to the first answer. So just like a Taylor expansion, the first answer is really a leading order, and the second answer is we would consider this is the next to leading order. So there is actually no conflict between what we know about this problem, right? So good. So I think the x goes to infinite limit should be reasonable, and I hope you can also convince yourself like what really happened at this large x limit. Now, what really gets interesting is that here we are not only talking about a bunch of point charges. We can generalize this point charge to a charge distribution. So say that in mathematics, when we can, as long as this function is smooth, we can transform a discrete sum to an integral, right? We can do the same thing by changing the sum of the charges to an integral of the charges. And this integral of charge can be either one-dimensional charge, so it's a line charge. So you can think of a straight wire and all the charge sitting at the wire. And it can also be a surface charge, right? You can think of a plate of metal, and there will be a charge on this metal. And you can also think of a volume charge, where you get a bulk of metal, and there might be a bulk of material, and this material might have some charge density distribution within the material itself. And so in this case, we are considering the possibility of line integral, right? Here, the line integral density, we typically write down this charge density as lambda. And also a surface integral, where we typically write the charge density as a sigma. And finally, we have the volume integral. The charge density is typically written as rho. And again, we are doing physics, not mathematics. And when we are talking about this charge density, please make sure that we are on the same page about the units. And so even though they are all called charge density, really they are of different units. Because here the dq is of unit of dq is of unit of Coulomb, right? And so the same for dl prime sigma dA or rho d tau. However, this line has the unit of length, and this has the length square, length q. So you can see that the lambda should have the unit of Coulomb over length, which is meter, and so this one has the unit of Coulomb over length and Coulomb over length cubed, and do not mix all of these terms, and try to check your final result if the unit makes sense, and if not, you probably drop something somewhere. So just like what I did before. So here, so here initially I actually forget this r squared, and the unit didn't make sense. So somehow I try to fix this error, and I have to insert R square here. Otherwise, unit-wise, it doesn't work. Okay. Now let's try to do a simple example.